We're going to be looking at how to use partial derivatives to find relative extrema of functions of more than one variable. But before we do that, let's do a quick review of how we found relative extrema for a function of one variable. So this will be our example. Now to find relative extrema, we always took a derivative of our function, and then we looked for critical values by setting that derivative equal to 0 and solving for the values that make our first derivative equal to 0. Once we had our critical values, we needed to determine whether they represented relative maximums or relative minimums. And for the most part, we used a sign chart of our first derivative to tell where the function was increasing or decreasing, and that determined where we had maximum or minimum values. But there was a second way we could have found relative extrema, and that second way was the second derivative test. Now what the second derivative test said was that if we have critical values, in this case we're calling the critical value c, and we look at the second derivative at that critical value, then the critical value represents a relative minimum if the second derivative is positive at that critical value. In other words, if at that critical value our second derivative is positive, that means that our function is concave up. And the only way the function can be concave up through that critical value is if the critical value represents a minimum. And likewise, if the second derivative was negative at that critical value, then the critical value represented a relative maximum. And that's because the only way the function could be concave down at that critical value was if that point represented a relative maximum. Now to go back to this example one more time, remember we found these critical values, but we didn't know whether they represented relative maximums or relative minimums. If we use the second derivative, which in this case is 6x plus 6, and then substitute the critical values into the second derivative, we can figure out whether these are maximums or minimums. So negative 3, when we substitute it into our second derivative, gives us a value of negative 12, meaning the function is concave down at that point. So that means that when x is negative 3, we must have a relative maximum. And if we substitute 1 into our second derivative, we get a positive value, which means at that point our function is concave up. So we must have a relative minimum where x is 1. Now we're going to look at a function that has two independent variables and see how we can also use derivatives to find the relative maximum or relative minimum values. It's a slightly more complicated process, so let's just look at the steps we'll need to take before we actually try to find those values. So the first step we're going to have to do is find a whole bunch of partial derivatives. We'll find our two first partial derivatives, f sub x and f sub y, and we'll find 3 of the second partial derivatives. The next thing we'll do is set each of our first partial derivatives equal to 0 and solve those equations. The value that we get is going to represent a critical value. Then we'll find a number that we're going to call d. D is a number that we'll get by substituting the critical value into our second partial derivatives and then coming up with a number that we can then use to determine whether we have a relative maximum, a relative minimum, or a saddle point. Now it's also possible that the value of d would be 0, and in this case we really can't say whether that critical value represents a relative maximum or a relative minimum. So let's go back to this function and go through those steps. So the first step is to find a bunch of partial derivatives. So let's start with the first partial derivative with respect to x, and then we'll take our second partial derivative, f sub xx, and then we'll also find f sub xy. Then we can go back to our function and find the first partial derivative with respect to y, f sub y. And then we can find f sub yy from that. And now we have everything we need. We have all of our partial derivatives. So now we'll take our two equations that we had for our first partial derivatives, and we'll set them both equal to 0, and we'll solve those equations. Now that should remind you of exactly what we did before when we were finding critical values. We took a first derivative and set it equal to 0. Now we're just taking our first partial derivatives and setting them equal to 0. Now what you probably notice is that both of these equations have an x and a y in them, which means we have a system of equations that we're going to have to solve. So just a little reminder, there's several methods for solving a system of equations. We could use elimination, we could use substitution, and either of those will get a solution for this system of equations. So for this particular one, let's use substitution. Let's take the second equation and solve it for x. And then since x equals negative 2y, we'll substitute negative 2y in the first equation for x. And then we'll solve that equation for y. And we have y equals negative 1. Now since we're trying to find an ordered pair, a value for x and a value for y, we'll need to substitute that negative 1 back into our substitution equation to get a value for x. So we have x is 2 and y is negative 1 as our critical value. Now to determine whether that critical value represents a relative maximum or a relative minimum, we have to find the value of d, which we get by looking at our second partial derivatives. So d is equal to the value of those second partial derivatives when we substitute 2 in for x and negative 1 in for y. But in this case, all of the second partial derivatives are constants, so we really have nothing to substitute in for an x or a y. We simply have to take the values of the second partial derivatives. So f sub xx is 2, f sub yy is also 2, and f sub xy is 1. So we need 2 times 2 minus 1 squared, which is 3. Now since d is positive, we have to look at the value of f sub xx to determine whether that's a relative maximum or a relative minimum. Since f sub xx is 2, which is positive, that means that the point represents a relative minimum. Now to find the actual relative minimum value, we'll have to substitute 2, 1 into our equation for x and y to in essence get the z value for this point that's in three-dimensional space. So we'll substitute 2 for x and negative 1 for y, and we get a value of negative 3. So our minimum value is negative 3, but in terms of where this fits on the graph of this function, it's the point 2, negative 1, negative 3. Now you're not going to be asked to graph anything in three-dimensional space, but to give you a better idea of what we've just done, let's take a look at the graph of this function and see if we can find this point 2, negative 1, negative 3 on the graph. Here's what the graph of the function looks like in three-dimensional space. So what you'll notice is that the x-axis is the red axis that's going more or less horizontally. The y-axis is the green axis, and then the z-axis is the vertical axis. Now what we're going to do is move this around just a little bit before we start to play with it. So let me just rotate it a little bit, and you can see what this looks like. Now remember, what we were trying to find was the relative maximum or relative minimum value, and you can see that there is a lowest point on this graph. That's the point that we found. Now when we did those partial derivatives, what we were doing was looking at what happens when we take a plane and slice through this graph with the plane. So let's see what those planes would look like. So here's one plane. Let's move it a little bit so that you can see that it is intersecting our curve, our three-dimensional curve. And if we highlight where it's intersecting, you might get an even better idea of what's going on. Let's rotate this a little bit again so you can see what's happening. So you can see that yellow line, that yellow curve, I should say, that's intersecting our three-dimensional figure here. That's what we're looking at, and it looks like a parabola, doesn't it? So what we're trying to find out is where that is the lowest point on the graph, which looks like it's right about there. But since this is three-dimensional, we have to look at it in more than one direction. So let's rotate this a little bit more again, and let's cut through this with a plane in another direction. That's basically what we were doing when we were using our first partial derivatives. We were just looking at a plane that was cutting through the graph. So now you can see this green plane that's cutting through the graph, and it also seems to be cutting through and making something that looks kind of like a parabola. And if we look at where it's intersecting this three-dimensional space, you can see, sure enough, that does look like a parabola. So let's maybe move it like this. And let's see if we can make that go down to where it seems to be hitting the lowest part of this curve. Looks like right about there. So with our first partial derivatives, we were in essence cutting through this three-dimensional shape, but we were cutting through it with these planes, and we wanted to know what were the minimum values in each direction. So we'll put both of those back on here, and then let's rotate this a little bit. We're trying to figure out where that low point is. If we look through right through the top of it, so let's put this back so that when we look straight down through the top, we're going to see the X and Y axis oriented just like we're used to seeing them. Look at where those are intersecting. They're intersecting at 2, -1. And remember, that was what we got when we solved that system of equations, those first partial derivatives. We got 2 for x and -1 for y. And then we had to determine whether that represented a maximum or a minimum value. That's what the second derivatives told us. The second derivatives told us something about how this particular shape was curved. So we determined that we had a minimum value, but then we substituted those values back into our function to get a z-coordinate. And look at how low this goes. This goes down to -3, which was the z-coordinate we got when we substituted our two values for x and y, which were 2 and -1. We substituted those into our function. So let's look at a new function and see if we can go through this process again. We said that we need to find our partial derivatives. So we'll find our first partial derivative with respect to x and with respect to y. And then from each of those we'll find some second partial derivatives. We'll find f sub xx, f sub xy, and f sub yy. Then we'll set each of our first partial derivatives equal to 0 and solve that system of equations. Remember, we've got two methods that we can use to solve these systems. We could use elimination or we could use substitution. So for this one, let's try elimination. We'll take the first equation and we'll isolate the variable terms on one side and the constant term on the other. And then the second equation already is in that form, so we have to decide which variable we're going to eliminate. So let's say we decide we want to eliminate the y's. We could do that by multiplying both sides of the first equation by -4, and then adding that to the second equation, which would eliminate the y's and give us an equation which we can solve for x. So we have x equals 4. Then we can substitute 4 into any one of the equations that we started with, or that we had once we rewrote the equations. So we'll substitute this in the second equation, x plus 4y equals 0, and we get y equals -1. So we do have a critical value where x is 4 and y is -1, but we need to determine whether that critical value represents a maximum, a minimum, or a saddle point. The value of d is going to give us that information. So we need our second derivatives, and we need to find the value of those second derivatives at this critical point for -1. Once again, our second derivatives have no variables in them. So f sub xx is just 2, f sub yy is just 4, and f sub xy is just 1, which gives us a value of 7 for d. Now, since d is positive, that means there's either a maximum or a minimum at 4, -1, and since the second derivative is also positive, that tells us that the point where x is 4 and y is -1 represents a minimum. And to find the z-coordinate that goes along with that x and y, in other words, to find that actual minimum value, we'll substitute 4 for x and -1 for y in our function, and we'll get a z-coordinate of -14. So this function has a minimum value at the point for -1, -14, and the minimum z-value is -14. Let's try this one. The process doesn't change. We're still going to find our first and second partial derivatives. Our first partial derivative, f sub x, is y minus 3x squared. F sub xx is -6x. F sub xy is 1. Our first partial derivative, f sub y, is x minus 2y, so f sub yy is -2. To find the critical values, we need to set our first partial derivatives equal to 0 and solve that system of equations. Remember, we can either use elimination or substitution, whatever seems to work best for you. In this case, let's use substitution. So we can solve that first equation for y. So if y equals 3x squared, we can substitute 3x squared in the second equation for y. And then we have an equation that just has x's in it. So we can solve that equation. If we factor an x out, set the factors equal to 0, we get two solutions for x, 0 and 1/6. So to find the y that goes along with each of those x's, we can substitute those values in our equation y equals 3x squared. So when x is 0, y is also 0. And when x is 1/6, y is 1/12. So this time we have two critical values, 0, 0, and 1/6, 1/12. Now we need to find this d for each of the points, but we need to do it one point at a time. So for 0, 0, we need to look at our second partial derivatives. Now in this case, you'll notice f sub x does have a variable in it. So that means that when we find the value of d, and we're looking at f sub x, we have to substitute 0 for the x in f sub x. F sub y and f sub xy are just constants. So when we simplify, we get -1. Now if d is negative, that means it's less than 0, which means this represents a saddle point. To find its z-coordinate, we still need to substitute our critical values, 0 for x and 0 for y, in our original function. And we get the z-coordinate of 0. So we know there's a saddle point at 0, 0, 0. Now back to the second point we found. We had 1/6 for x, 1/12 for y. To find the value of d, we'll have to substitute 1/6 in for the x that we see in f sub x equals -6x. Since f sub y and f sub xy are both constants, there's nothing to substitute into those second derivatives. And when we simplify, we get a value of 1 for d this time. So since d is positive, that means our function either has a maximum or a minimum at this point. To determine which it is, we look at the value of f sub x at that point. So f sub x when x is 1/6, -6 times 1/6 is -1, which is less than 0, which means that this point represents a maximum value. And to get its z-coordinate, we can substitute 1/6 for x and 1/12 for y into our original function, and we'll get a value of 1 over 432. So we have a maximum at the point 1/6, 1/12, and 1/432. All right, let's try one last problem. Once again, relative maximum and minimum we'll find exactly the same way. We'll find our first and second partial derivatives. So f sub x is 3x squared minus 3. F sub y is 2y minus 4. F sub xx is 6x. F sub xy is 0. And f sub yy is 2. Now we'll have to solve the system of equations that we get when we set each of our first partial derivatives equal to 0. And in this case, this is actually a little bit easier, because you'll notice both of these equations only have one variable. So we don't have to solve this with elimination or substitution. We can simply solve each of the equations separately. So if 3x squared minus 3 equals 0, then 3x squared equals 3, x squared equals 1, which means x is either positive 1 or negative 1. And if 2y minus 4 is 0, then y is 2. So we got 2 x values and 1 y value, so that y value needs to be paired with each of those x values to give us 2 critical values, 1, 2, and -1, 2. So we'll have to find d for each of those points. For the point 1, 2, we need to find f sub x of 1, 2, which means substitute 1 into f sub x where you see that x. So 6 times 1 is going to be 6. F sub yy is 2 minus f sub xy squared, 0 squared. So we get a value of 12. Since d is positive, the function either has a minimum or a maximum at that point, but since f sub x, which is 6x, is 6 times 1, that's positive, so that means we have a minimum at that point. To find the minimum value, we'll substitute 1 for x and 2 for y in our function, and we get a value of -3. In terms of three-dimensional space, the minimum occurs at 1, 2, -3. Now the other point was -1, 2. We'll do exactly the same thing. We'll find f sub x at that point, which means we need 6 times -1. We know f sub y is 2 and f of xy is 0. So we get a value of -12 for d. So since d is negative at this point, that means we have a saddle point. And to find the z-coordinate, we still substitute -1 for x and 2 for y in our function, and we get a z-coordinate of 1. So our saddle point is at -1, 2, 1. So let's look at this graph. Remember, we had a saddle point. So the saddle point is a high point in one direction and a low point in the other. And we had a minimum, which is a low point in two directions. So if you look at how these planes intersect our curve, you can see that in this case, on the right side, when the plane's intersecting the curve, it's a high point, then it's a low point. And now if you look at the intersection that's coming up on the right side, we have a low point intersecting the plane and another low point. So that would be our relative minimum value. So don't rush yourself as you're working through these problems. There's lots of places where it would be very easy to make a mistake. So just give yourself the time to work through the problems very cautiously so that you don't make those mistakes.